All right, so we're moving on to lesson 4, and in lesson 4 we're going to look at solving exponential and logarithmic equations. Um, exponential equations are simply going to be equations where the variable is in one or both of the exponents. Okay, so anytime you have an example or problem where your x's are in the exponent, you've got an exponential equation. Logarithmic equations are pretty obvious because they have logs in them. So we're going to start out with solving exponential equations where, in this case, if you notice, the bases are the same. You have 7 to the 3x power equals 7 to the 2x plus 5 power. Really what you're looking for is the value of x that makes those two exponents the same. So when the bases are the same, it's a pretty simple process. Set the exponents equal to each other. So when the bases are the same, set the exponents equal and solve for the variable. So here, x equals 5. And to make sure that that is true, if I substitute 5 for x, that gives me 7 to the 3 times 5 equals 7 to the 2 times 5 plus 5. And this is 7 to the 15th. This is 7, that doesn't look like a 15. And this is also 2 times 5 is 10, 10 plus 5 is 15. So it works. So the solution is x equals 5. When the bases are the same, it's just a matter of setting the exponents equal to each other and solving for x. Now the next example is a little different in that the bases are not the same, but we can make them the same. If you can take the bases and get them to be the same, then it's just a matter of setting the exponents equal. Now when you have an exponential equation, you cannot make a base bigger, but you can make a base smaller. So this 3 to the 5x minus 8 is going to stay as is. But this 9 can be written in terms of 3. We can write 9 as 3 squared, and that's raised to the x plus 2 power. Now what we have is 3 to the 5x minus 8 equals 3. Now we have to utilize our properties of exponents. When you raise a power to a power, you get 3 to the 2x plus 4 power. Now the bases are the same, so we can drop the bases and set the exponents equal. So 5x minus 8 equals 2x plus 4, and we're ready to solve. So subtract the 2x, we get 3x. Add the 8, you get 12, x equals 4. And if you substitute 4 for x here, that's 5 times 4 is 20. 20 minus 8 is 12, so that's 3 to the 12th power. That's 3 to the 12th. And then when you substitute 4 for x, you get 4 plus 2 is 6. 9 to the 6th power and 3 to the 12th power should be the same. So let's just check that. 3 raised to the 12th is 531,441, and 9 raised to the 6th power, same thing. So if you can make the if you can make the bases the same, then all you have to do is set the powers equal to each other. But if you change the bases, one or more of them, your exponents are going to change. They have to. All right, so next example, we notice that we have a 4 raised to the x minus 3 power. We also have an 8 raised to the 4 minus x power. So let's talk and see if we can make our exponents, not exponents, but can we make the bases the same? Well, your first thought might be to take 4 and square it to get 8. 4 squared is not 8. 4 squared is 16. What if we changed both of these to 2? Our 4 can be written as 2 squared raised to the x minus 3, and 8 can be written as 2 to the third raised to the 4 minus x. So we've written this example or this equation where they have the same base. Now let's apply the properties of exponents. So that's going to give us a 2 to the 2x minus 6 power equals 2 to the 12 minus 3x power. So our bases are the same. So we'll drop the bases and set 2x minus 6 equal to 12 minus 3x, and I can solve for x. I will add the 3x over, that gives me 5x. I will add the 6 over, that gives me 18. So x equals 18/5. And so that's our answer. All right. So the key is if you can get your bases to be the same, then do so, because then all you have to do is set your exponents equal to each other. All right, so then we have another exponential equation. We have 9 raised to the x squared power equals 3 to the 3x plus 2 power. So let's take that 9 and write it in terms of 3. So 3 squared to the x squared power will equal 3 to the 3x plus 2 power. All right, applying the properties of exponents, raising a power to a power, we will multiply. That gives me 2x squared equals 3x plus 2. I kind of did two things at one time there. I raised a power to a power here, I multiply those, and then set those two equal. Pardon me. So now you notice, hopefully, that we don't have a linear equation, we have a quadratic equation. So we're going to use this quadratic equation to help us solve this exponential equation. So quadratics, we typically will start with everything on one side. So take your 2x squared, subtract the 3x, and subtract the 2 and set that equal to 0. And then I think this one will factor, and it will factor into 2x and x. I need a 3 in the middle. I'm going to put a 2 here and a 1 here and a minus and a plus. So your factors are going to be 2x plus 1 times x minus 2. Let me make sure of that. -4. Yeah. So solving a quadratic equation, you take your two factors, you set them equal to 0, and you solve each factor. So you get one solution as -1/2, you get another solution of 2. So x equals -1/2 and x equals 2. If you substitute each of those individually into the problem, original problem, you would get solutions that work. So again, if you can get your bases to be the same in an exponential equation, then all you have to do is drop your bases and set your exponents equal and solve. All right, so let's take a look at this one. This one looks pretty complicated, but I see a 9 to the 2x times a 1/3 to the x plus 2. I see 27 times a 3 to the x to the -2. So these bases look like they could all be written in terms of 3. 9 is 3 squared. So that's going to be 3 squared to the 2x times 1/3 can be written as 3 to the negative 1 power to the x plus 2 power. 27 can be written as 3 to the 3rd multiplied by 3 to the x to the negative 2 power. All right, I'm going to raise the power to a power here, power to a power, power to a power. So this is 3 to the 4x times 3 to the negative x minus 2 equals 3 to the 3rd times 3 to the negative 2x. So on the left side, I have 3 to the 4x times 3 to the negative x minus 2. So I'm multiplying, so I will add the exponents. I'm going to also, at the same time, drop the bases. But please be careful when you do this. So 4x plus negative x, that's going to be 3x minus 2 equals, here I will multiply, I'm multiplying, so I will add my exponents, so that gives me 3 minus 2x. So I will add the 2x over, I will add the 2 over, and it looks like I have 5x equals 5, so x equals 1. Ooh, okay. So x equals 1 is my solution. Now, if I double check this, x equals 1, 9 to the 2x, so 2 times 1 is 2, so that's going to be 81 times 1 plus 2 is 3. 1/3 to the 3rd power is going to be 1 over 27. Over here, we have, if I substitute 1 here, this gives me 3 to the negative 2nd power. So I'm looking at 27 times 3 to the negative 2. Okay. 3 to the negative 2 would be 1 over 9. 27 over 9, does that equal 81 over 27? 81 over 27 equals 27 over 9. Let's think about that. 9 will go into 81 9 times. That reduces to 3. No, it doesn't. Yes, it does. And 27 over 9 reduces to 3 also. So you can always check yourself. I know you don't want to, but you can still always check yourself. Okay. So let's take a look at some logarithmic equations, some pretty basic logarithmic equations. You have log base 7 of x minus 5 equals log base 7 of 6x. Now, what's nice about this example is that both of the logs have a base of 7, which makes things really nice. I have a single log on each side of this equation. I have log base 7 of the x minus 5. I have log base 7 of 6x. So really what I'm looking for is what value of x will make this expression and this expression the same. So since the bases are the same, I can just drop the logs and set x minus 5 equal to 6x and solve for x. So I think what I'll do is I will subtract the x, and that's negative 5 equals, what is that, 5x, and x equals negative 1. So I got some bad news to tell you. Something that you're not going to want to hear. But the deal here is this. When you're solving a logarithmic equation, you absolutely have to check your answers. Because sometimes you might do everything correct in the solving process, but the solution that you get is not a solution to that particular logarithmic equation. So this one falls into that category. When you solve, or when you check -1, n for x, let's talk about what we have. We have log base 7. You put your -1 minus 5 in there equals log base 7 of 6 times -1. Now, if you look at this, this is all nice and pretty. You get log base 7 of -6 equals log base 7 of -6, which looks like the solution works. However, if you remember, what do we remember about this part of this expression? That part of the expression has to be positive. This expression right here, in both of those, have to be a positive expression. Well, they don't turn, the -1, when you substitute -1, you get a negative value. So even though mathematically you worked through this and got a correct value that appears to solve this linear equation, this is the linear equation, the -1 works for the linear equation, but it does not work for the logarithmic equation. So if x equals -1 is the solution that we got and it doesn't work for this, then guess what? This equation has no solution. So there is no value for x that would ever make that equation true. Oops. Okay. All right. All right, so now we have, let's look at example 7. Example 7, we have the natural log of x squared equals the natural log of 12 minus x. The left side of this equation has a single log, so does the right side. And they're both natural logs, which means they have the same base, so we can drop our logs and set x squared equal to 12 minus x. Okay, I didn't really have to put that in parentheses, I just did. So here we have a quadratic, so we're going to use this quadratic to help us find the solutions to the logarithmic equation. So this is a quadratic, I'll get everything on one side. So x squared plus x minus 12 equals 0. I will factor x plus 4 times x minus 3 equals 0. So my solutions for the quadratic are x equals -4 and x equals 3. All right, so let's talk about these two solutions. These two solutions are definitely solutions to this quadratic. Are they the same? Are they solutions? Are they both solutions to the original? Well, when you substitute, you get your natural log of -4 is being squared, and that equals the natural log of 12 minus 4, or 12 plus 4, sorry. When you put the negative in there, it's 12 minus -4. When you square -4, you get positive 16. So -4, and on the right, you also get the natural log of 16. So x equals -4 does work. Same thing for 3. If you put in the natural log of 3 squared, that's going to give you the natural log of 9. And when you substitute 3, 12 minus 3 is 9 also. So both of these are solutions to the natural logarithmic equation as well. Okay. All right. Maybe you have a good a good feel for solving logarithmic equations where the bases are the same, as well as exponential functions where the bases are the same. The idea in both of those cases is to either drop your bases or drop your logs so that you can solve for the variable. All right, so nothing fancy for this one. You have a single log on both sides of the equation. The bases on those logs are the same, so we'll set x squared equal to negative 3x minus 2. And this is a quadratic, so get everything on one side. That will be x squared plus 3x plus 2 equals 0. And that will factor into x plus 1 times x plus 2 equals 0. So the solutions for the quadratic are x equals negative 1 and x equals negative 2. Are they the same? Do they work rather for the logarithmic equation also? So let's see. If I take my negative 1 and put it in for x here and square it, that gives me positive 1. If I take my negative 1 for x here, negative 3 times negative 1 is 3, and 3 minus 2 is 1. So the negative 1 works. How about negative 2? Negative 2 squared, we said, is 4. Negative 3 times negative 2 is 6, and 6 minus 2 is also 4. So these are the two solutions for the logarithmic equation. All right. All right, so let's go ahead. We're going to do the last three examples. Here we have the natural log of log base 3 of 2x minus 3 equals log base 3 of 9. That's pretty straightforward. The logs are the same. Drop the logs. Set those equal. Solve for x. So that's 2x equals 12. So x equals 6. Checking this, 2 times 6 is 12. 12 minus 3 is 9. And both of those equal. All right, now there's one little twist on example 10. Notice that on example 10 has a coefficient for one of its coefficients, or for one of its logs. Here I've got 2 times log base 5 of x equals log base 5 of 9. So here's where your properties come in. Just like up here we had to use properties of exponents, here we're going to use properties of logarithms. Since this equation, or this logarithm, has a coefficient of 2, we will rewrite this as log base 5 of x squared equals log base 5 of 9. So pretty simple. Drop your logs since the logs have the same base, and we have x squared equals 9, which means x equals plus or minus 3. All right, so you have to check your solutions. Even though positive and negative 3 work for the quadratic that we have here, we have to check them. I'm going to go ahead and just say, let's check the negative 3. If you take that negative 3 and put it back into the original expression, that should be an log base 5 of negative 3 equals log base 5 of 9. Because the negative 3 in the original form of the logarithm, because it makes this negative, negative 3 is not a solution to this equation. And I know what the argument will be, but if you take it and plug negative 3 into this version, you do get positive 9. And I will agree with you. But the key to testing whether or not a solution for the quadratic is also a solution for the original logarithmic function is you have to substitute it into the original. All right. So, so really, I think by now you kind of have the idea that when you have a logarithm or logarithmic equation, if you can get your equations, if they are a single log on each side of the equation and the bases are the same, you can drop your logarithms and then solve for the variable. Here, I think this is just a pretty straightforward example, which is the one that will stop this portion of the video on. We have log base 3 of 3x minus 6 equals log base 3 of 2x minus 1. The bases on the logs are the same, so I can drop the logs and set 3x minus 6 equals 2x minus 1, and I can solve. Subtract the 2x, I get x, add the 6, I get 5. So checking, 3 times 5 is 15, and 15 minus 6 is 9. Let's see if it turns out to be 9 over here. 2 times 5 is 10, minus 1 is 9 also. So this is your solution as well. Oh, over here I did not write it clearly, but x equals 3 only is the solution. I need to make sure that I specify that. So this is where we're going to stop this video in this part of the lesson to get practice on working with equations that have exponents where the bases can be the same, and logarithms that have the bases that can be the same as well. So this is where we'll stop, and